Welcome to Electronics, the story of one human lifetime, presented by David Beams and Gary James. I am David Beams, and I am a retired associate professor of electrical engineering. The purpose of this series of presentations is to give our viewers a look at the incredible progress that took place in the field of electronics in what would be a typical human lifetime. We will be developing simple explanations of the theory behind these devices, and then showing examples of historic electronic devices from primitive vacuum tubes to incredibly sophisticated microprocessors. It goes without saying, the transformation of human life through technological innovation in the 20th and 21st centuries has been profound, and electronics has been at the center of the action. Not only have there been stunning advances in electronics, but electronics now underpins the technologies that are integral to human life today. One day we believe that history will show that the invention of the field effect transistor was just as transformative as the invention of movable type or the wheel. The dawn of electronics begins, like many electrical things, with Thomas Edison. Edison is often erroneously credited with inventing the incandescent lamp. His contribution was to make a practical incandescent lamp, but we will let him speak for himself. He was just trying to improve his incandescent lamp. The glass envelope was getting darker as the lamp operated. Material from the filament was collecting on the glass, and he thought that a new electrode and a battery might be a solution because, well, that was his method. You just try something until it worked. And Nikola Tesla wants to know, so what happened? Let's let Edison tell us himself what he found. He added a battery in a milliammeter. He tried connecting the positive terminal of the battery to the hot filament, the negative terminal to the new electrode, and nothing happened. End of the story? Well, let's let Edison continue the story. No, he tried again. Maybe reversing the battery would make a difference. And he connected the negative terminal of the battery to the hot filament, and the positive terminal to that new electrode. And this time, his meter showed an electric current was flowing. So current in a vacuum? No. Yep, current flowing in a vacuum, but only if the new electrode was positive relative to the filament. Reverse the polarity of the battery, no current. The lamp acted as a one-way electric valve. He had no idea what to do with this, but he filed a patent anyway, which was sort of what Thomas Edison would usually do. Yeah. What Edison had discovered, the one-way flow of electric current in a vacuum, was called the Edison Effect, and it was inexplicable at the time. So enter J.J. Thomson, British physicist, experimenting with a Crookes tube, an apparatus like this. A Crookes tube was an evacuated glass tube with two electrodes sealed inside. Notice the slit in the anode, the positive electrode. When a high voltage was placed between the electrodes, a fluorescent screen at the other end of the tube would glow, evidence that some sort of radiation, what was called cathode rays, was being emitted from the electrodes. Deflection measurements allowed Thomson to estimate the charge to mass ratio. What Thomson had done was demonstrate the existence of the electron. Let's let Tesla sum it up for us. Electric currents were flows of charged particles. Now we knew why electric current in a vacuum could happen. High voltage caused emission of electrons from the cathode in the Crookes tube, but in Edison's lamp filament, electrons were produced by thermionic emission. So now we're going to create a simple physical analogy to explain the Edison effect. We begin with a system like this. We have a pipe or tube open at the top containing balls of lightweight plastic, like styrofoam. We have a port at the bottom emitting air under pressure, a valve to control the airflow, which for the moment it's closed. Gravity draws the balls to the point of lowest gravitational potential energy, in other words, to the bottom of the pipe. Now let's consider an electrical system. We have an unheated filament sealed in a vacuum. Just as gravitational forces bind the styrofoam balls to the bottom of the pipe, electrostatic forces bind electrons to the filament. The filament is electrically neutral, containing as many positive as negative charges. Now we're going to activate each system. We open the valve, admitting air. The balls are propelled upward, but the tube is so tall that none of the balls escape. The balls are also falling back down to lower gravitational energy states by the force of gravity. These two processes reach an equilibrium, and the tube fills with what we might call a ball gas of balls in constant motion. Now let's examine the electrical system. We apply an electric current to heat the filament, liberating electrons which cannot escape from the enclosure. Now, the net positive charge of the filament creates an electrostatic forces that draw electrons back toward the filament. The boiling off and reabsorption processes reach an equilibrium, creating an electron gas in constant motion surrounding the filament. Now we're going to modify these systems. Now we have the balls held in a reservoir inside the pipe. There's a drain at the bottom of the pipe representing lowest gravitational potential energy, and a conveyor that collects balls from the drain and returns them to the reservoir. Now let's consider a modified electrical system. The filament acts as an electron reservoir. The drain at the bottom of the vacuum enclosure is at the lowest electrostatic potential energy for electrons. The battery, note the polarity, produces an electrostatic potential that puts the drain, which we call the plate, at this low energy. Now, a little note concerning the drawing. Gravity has a negligible effect on electrons, but putting the drain at the bottom is a way of saying or conveying the idea that the plate is at the lowest electron energy. The battery serves as an electron pump or conveyor to return electrons from the plate to the filament. Now we're going to activate these systems. Okay, it's a physical system with airflow. The reservoir becomes a ball fountain. The balls fall to the bottom of the pipe. They're collected at the drain. And the conveyor returns the balls to the reservoir, and this enables a steady state process, a continuous flow of balls. Now let's activate the modified electrical system. The hot filament provides an electron fountain. Electrons are attracted to the drain, which we also call the plate. The battery returns the electrons to the filament, enabling a steady state system. In other words, a continuous flow of current through the external circuit. Now we have an analog to explain conduction in the Edison effect. We'll modify our mechanical and electrical systems to demonstrate why this conduction was unidirectional. Here's the mechanical system. We've moved the drain higher than the reservoir, putting the drain at a higher gravitational potential energy. When the fountain is activated, only a few balls gain sufficient kinetic energy to reach the drain. If the drain were high enough, no balls would reach the drain, and the flow of balls in the return path would be zero. In the electrical system, we'll make the plate negative with respect to the filament, and the plate is now at a higher electron energy than the filament. Few electrons leave the filament with enough kinetic energy to overcome the energy barrier to be collected at the plate. If we make the energy barrier large enough, no electrons can reach the plate. So we've used a mechanical analogy to explain the one-way current flow discovered by Edison, but he found no practical use for it. But this fellow did. J.A. Fleming in the United Kingdom produced a two-element vacuum tube, which he called a valve, for use as detectors in radio receivers. This photograph shows some early Fleming tubes. In the UK, the term valve became attached to any kind of vacuum tube, not just this two-element tube, which later became known as a diode. And here is a copy of Fleming's patent on his valve. But the major breakthrough in tubes, the next giant step forward, was what was known as the audion. It opened the door to modern electronics. The inventor of the audion was Lee de Forest. He's shown in this photograph circa 1921 holding examples of his audion. On the right, we have an early audion. The modification that made the audion was a third electrode that was called the grid. A negative voltage was applied between the grid and the cathode. The plate current could be modulated by the grid to cathode voltage. This was important. And let's see why this property was so important. Now here we have a schematic diagram of a circuit involving an audion. Let me walk you through the elements of the circuit. This represents the audion itself, this circle with this enclosing these elements inside of it. This represents the plate. This represents the grid. This is the cathode. And here we have a battery for heating the cathode, a grid to cathode voltage. We have here the plate current, represented by this arrow. We have the battery voltage, and we have a resistance in series of the plate, or the plate resistance. And lastly, we'll designate the plate to cathode voltage. Now, I'm going to involve a small amount of mathematics here, not a daunting amount, but a little. If we invoke Kirchhoff's voltage law and Ohm's law, which you'll learn about if you haven't already in your introductory circuits classes, we can write an equation that relates the plate to cathode voltage to the battery voltage, the plate current, and the plate resistance. The plate to cathode voltage is equal to the battery voltage less the voltage dropped across the plate resistance, which is the product of the plate current and the plate resistance. Now let's assume that somehow I can make a change in the plate current. We'll call that delta IP. That's going to produce a corresponding change in delta VPK. In other words, if I change the plate current, it's going to change the plate to cathode voltage. And if I subtract the steady state quantity from this equation, I get an equation that relates the change in the plate to cathode voltage with the change in the plate current. And it's simply minus the change in the plate current times R sub P. Now let me explain briefly what the minus sign signifies. It simply means that these two quantities, the change in the plate current and the change in the plate to cathode voltage, go in the opposite direction. If I make a positive change in the plate current, an increase in the plate current, that increases the voltage drop across the plate resistor, and the plate to cathode voltage must decrease. So a positive change in the plate current makes a negative change in the plate to cathode voltage. Similarly, if the plate current goes down, I have a negative plate current change. I get a positive change in the plate to cathode voltage. That is the significance of the minus sign here. Now, let's define the change in the plate current as this ratio, change in plate current divided by the change in the grid to cathode voltage multiplied by the grid to cathode voltage. And I'm going to take this quantity, change in plate current, with respect to the change in the grid to cathode voltage, and assign it the symbol G with a subscript M. And I'm going to give it the name transconductance. And where transconductance comes from, it's a mashup, if you will, of transfer and conductance. The voltage between the grid and the cathode, a change in that voltage causes a change in the current flowing through another branch of the circuit. If a voltage in one place causes a change change in voltage in one place causes a change in current in another. We call that a transfer conductance, but that's too long, so we just say transconductance. So I can then rewrite the expression for the change in plate to cathode voltage as minus the transconductance times the change in the grid to cathode voltage times the plate resistance. Now let's form the ratio of the change in the plate voltage to the change in the grid to cathode voltage, and it's minus GM times RP. This little equation is huge, because if the product of the transconductance and the plate resistance is greater than 1, then the magnitude of the change in the plate to cathode voltage is greater than the magnitude of the change of the grid to cathode voltage that caused it. In other words, the signal VGK, which we'll treat as the input, is amplified. If I treat this as the output of my circuit, the output voltage is larger than the input voltage. We have an amplifier. The criterion for amplification is that the product of transconductance and plate resistance must be greater than 1. So, amplification was the door to modern electronics. One of the things it provided was vastly more sensitive radio receivers. Before the audion, the energy required to activate the listener's headphones had to be gathered entirely from the traveling radio wave. It also made possible sound on film or talking pictures, and it made possible long-distance telephone service. Before the audion, practical range of a telephone system was limited by the resistance of the wires. The audion extended the range by means of repeater amplifiers. Some other applications that were only made possible by the ability to amplify: oscillator circuits for converting DC voltages into AC voltages at defined frequencies. This ability and the much greater sensitivity of radio receivers made broadcasting possible. We will turn now to some analogies to explain the behavior of the audion. So let's consider the physical system in which styrofoam balls are being held in the reservoir. The sides of the reservoir form an energy barrier. Balls with sufficient kinetic energy from the pressurized air coming in can escape from the reservoir. Less energetic balls do not. They may be lifted up and fall right back into the reservoir. But in this case, the barrier is rather low and most of the balls surmount it and escape. They fall to the bottom. They're collected at the drain and returned to the reservoir. This system will operate continuously. Now let's modify the reservoir by making the sides higher. Fewer balls can escape from the reservoir, which reduces the flow of balls through the conveyor. And it makes intuitive sense that if we make the sides of this reservoir high enough, no balls will escape from the reservoir, and the flow in the return path will be 0. So let's consider extending this analogy to our modified electrical system. The negative voltage applied to the grid produces an energy barrier that only electrons possessing sufficient kinetic energy can overcome this barrier. The ability to raise or lower this barrier determines how many electrons can jump over the energy barrier. Making the grid more negative raises the barrier and decreases the electron flow. Making the grid less negative reduces the energy barrier and increases the current flow. The term audion didn't last long. It was replaced by triode, a designation for a 3-element vacuum tube. Electrical engineers make drawings of circuits using symbols to represent electronic devices. We'll look at the symbol for the triode. Here we have the plate, the grid, the cathode, and the heater. This is an indirectly heated cathode, in which the cathode was heated by passing an electric current through a separate heater. Some vacuum tubes used directly heated cathodes. Now, I said this is a triode, a 3-element vacuum tube, but there seem to be 4 things in this diagram. We didn't count the heater as an element of the tube, so this is still a 3-element tube, therefore a triode. A triode with a directly heated cathode would require a minimum of 4 external connections, but a triode with an indirectly heated cathode would require 5. Now let's take a look at the electrical behavior of a typical triode vacuum tube, in this case a type 12AT7, which was introduced in 1947. We have here the plate current in milliamperes on the y-axis and the plate to cathode voltage on the x-axis. We have separate curves of plate current versus plate voltage for each of 11 different grid voltages from 0 to -10 in increments. And it looks like they didn't include the complete complement of them. Looks like it jumps from -8 to -10. My problem. Okay, anyway, we have separate curves for grid voltages ranging from 0 volts to -10 volts. Now let's look at the effect that the grid voltage has on plate current. And what we'll do is we'll pick a plate voltage, and let's take 200 volts, and we will look at the plate current versus grid voltage at a constant 200 volts. If we have a grid to cathode voltage of 0, we have 22.5 milliamperes. But if we make it more negative, make it a -1, you see the plate current drops to 12.5 milliamperes. And if we go to -2 volts, it drops to 6 milliamperes. If we go to -3 volts, 2 milliamperes, and at -4 volts, it's down to 1 milliampere. The ability of the grid voltage to modulate the plate current is evident from this series, or this set of graphs. But the triode had a limitation. The triode's ability to amplify at high frequencies like radio frequencies was limited by electrostatic coupling known as capacitance between the plate and the grid. This frequency limitation was imposed through a phenomenon that's known as the Miller effect, which you will study in electronics classes. The solution was to add a second grid, which was operated at a fixed positive voltage between the original grid and the plate. This grid functioned as an electrostatic screen, and hence the new grid was called the screen grid, and the original grid was renamed the control grid to distinguish between the two. The addition of the screen grid created a 4-element tube, which was called a tetrode. But the tetrode had a unique problem of its own. This graph shows the plate current versus plate voltage characteristics of a type 24 tetrode operated with a filament voltage of 2.5 volts and a screen voltage of 90 volts. The graph shows separate curves for plate current versus plate voltage for grid voltages from 0 to -6 volts in increments of -1.5 volts. The plate voltage varies in this graph from 0 to 500 volts. And there is an additional plot, an additional graph of screen current versus plate voltage with a control grid voltage of -3. Then note here, this region where plate current decreases as plate voltage increases. See these curves here? The negative slopes indicating that the plate current is falling as the plate voltage is rising. This behavior, this strange behavior, is known as negative resistance, and it causes unstable circuit operation. This phenomenon occurs when the plate voltage was less than the screen voltage. The screen voltage is 90 volts, and this phenomenon begins for voltages on the plate of right at 90 volts or less. Electrons accelerated by the plate voltage smash into the plate and dislodge other electrons by what's called secondary emission. And some of these electrons then flowed back to the screen. Notice that the screen current is increasing with increasing plate voltage in the negative resistance region. A solution to the negative resistance problem of the tetrode was the addition of a third grid between the screen and the plate intended to repel secondary emission electrons toward the plate. This grid was called the suppressor grid, and this tube with 3 grids was known as the pentode. The suppressor was operated at a low voltage, often ground or 0 volts. In some pentodes, the suppressor grid was internally connected to the cathode. These are the plate current versus plate voltage characteristics of the 6J7 pentode operating with a screen voltage of 100 volts. The negative resistance behavior is absent even when the plate voltage falls below the screen voltage. So let's let Nicola sum this up for us. Many variants of vacuum tubes with triode, tetrode, and pentode were the principal ones. There were many material and manufacturing challenges involved. And in our next presentation, we will display some of the amazing progress of the vacuum tube during its half-century of dominance in the field of electronics. Thank you, and join us for our next presentation, where we will show historic vacuum tube technology.